Hello, just a quick test of the audio. I wonder if anyone can hear me. Oh, I'm really sorry. Oh, I'm so sorry. I seem to have missed off the sound. I'm hoping that you can hear me from now. Uh, Whoa, sorry about that. Entirely my fault. Uh, so I got carried away and didn't check the comments, but there we go. Right. Hoping everybody can hear me now. Just looking for some thumbs up or something. If not, let me go. Aha, right. I'm just going back. So let me just go back really quickly now. Sorry about that. It is entirely my fault. So going back to Tycho Brahe and his measurement of the sky, which was about as good as you could get with that. We've all seen the cartoon, so good that that's there. And refractor, which Galileo used to revolutionize the night sky. He could see moons orbiting around Jupiter, so that was a huge change to things. He could see mountains on the moon and he could see sunspots. So it was a big step forward in just this one tiny bit of technology, made a huge difference. Again, sorry about the volume, just a stupid error on my part. But he didn't know quite what to make of Saturn. And reached our peak with a 40-inch refracting telescope at Yerkes. And just going back to where I was, so the big problem with this is this large piece of glass right up here, right towards the roof, just where you don't want it, really heavy. So maybe up to a ton of weight up there at the far end. Needs an enormous amount of construction to maintain it. Very thick glasses, has to be very pure to let all the light through. Any impurities will soak up the light, so that could be an issue. And there are other things like chromatic aberration. So nearly every, pretty much every professional telescope is now of the reflecting type, with a large mirror at the back here that does the collecting and focusing onto the eyepiece, or more commonly now just onto cameras and other things like that. Famously found by Newton, or made first by Newton. This is a model of Newton's early reflector, and got to some of the very large ones like this one, the Mount Palomar 200-inch reflecting telescope, extremely large. See here with a manta scale, that's pretty good. The other major thing that made a difference to observing, at least professionally, is the change from photographic plates to CCDs, or CMOS devices in these days. So this is a photo taken by David Malin a long time ago on the Anglo-Australian 3.9 meter telescope, so a huge telescope. He's a very famous astrophotographer. And this is one from Paul Money with a 180 millimeter one of the same object. You have to say probably David Malin's is slightly better, but not that much better. And certainly with just a slightly larger telescope, you can easily catch up with David Malin and his 3.9 meter telescope. And this is really all down to CCDs. They are just wonderful things for capturing light of all wavelengths pretty much these days. And their efficiency is so much better than photographic plates. Photographic plates catch between 0.5% and 4 to 5% of the light coming into the telescope. The best CCDs are up to about 90%. So they are hugely better and much better across the range as well. They capture blue light as well as they capture red light in general. So a huge change from using those. So why do we go so big? Why is this aperture fever? I'm sure some of you people in North Wales have also gone for very large telescopes, or the largest you can afford. And it's not magnification, as I'm sure you know, because if you just blow things up, they tend to get more fuzzy. There is an ideal eyepiece for any telescope and conditions, which gives you a very good image. And if you try and push it too much, it just deteriorates rather than getting better. And it's more difficult to focus and all these other things. So there are two good reasons. One is just light gathering. If you double the mirror size, you get pi r squared increase, so you get a square. So going from 5 centimeters to 10 centimeters, you go from 75 centimeters squared of collecting area to 300. And that lets you collect a lot more light more quickly. And in the end, it's light photons that we're interested. But the more useful thing for astronomers is the resolving power. So this is given by this formula here, which I hope is not too scary. So this shows how closely you can view two things and still tell them apart, basically. And this is what you see. If you focus on a star, you will not see a single point-like object of the star in general. You will see rings like this. This is done via a laser to accentuate the effect, but this is what you see with all telescopes. And this is all governed by this formula. So this bit here, sine theta, which you don't need to worry about, that's just the width of the blob, how blobby the blob is, basically. And the other things are the type of light. So this doesn't make much difference to most amateurs because red light and blue light are pretty much the same. So we don't really care about that bit. This is the thing that really governs it. This is the size of the aperture. So this is how big your mirror is or how big your lens is. Because this appears on the bottom part of the equation, the bigger this is, the smaller this is. So as this goes up, this goes down. So the bigger the aperture, the smaller your blob, and the easier it is to split stars or separate two stars apart. So that's why we love a bigger size. And this shows you it here. You clearly see two things on the top one, but by the time you get to the bottom image, they're sort of blurred together. And that's what happens with stars and telescopes in general. The other issue is just seeing. This is the atmosphere that's messing up all the images you're seeing, because it as the light passes through the atmosphere, different sort of heated bits of the atmosphere or different densities act like tiny little lenses, and they just distort the atmosphere. So there is a limit to even the biggest telescope, down to the seeing, how stable the atmosphere is, although we are now getting around that. Just going back to light gathering power, the bigger the mirror, the more light you can gather. And this is particularly important because a lot of professional astronomy, we're not really looking just at stars, we're looking at spectra. So we want to take the light from a star and split it up into red, green, blue, or even further than that. And if you've got a very faint star, you'll have an extremely faint spectrum. So the more you split your light into a spectrum, and we'd love to be able to split it into very fine spectrum because you can use that for all sorts of things, including detecting exoplanets and so on. That's why light gathering is really crucial. So that's a spectrum, and you can see the little lines in that. I think that's the spectrum of the sun. Well, actually, this is what the spectrum looks like. We don't need colour in it particularly, we just need to know the intensity of it. So I hope everybody's still with me. Right, so now you all know what telescopes are like and how they work, which I'm sure everybody did anyway. Let's look at the state of the art. So let's start with one of the workhorses of professional astronomy. This is the SDSS, the Sloan Digital Sky Survey. It's been taking images for, I think, at least over 20 years. This is what's called a survey telescope, so it doesn't actually go off and look at anything particular. it surveys the sky. It takes pictures of the sky every night in just a sequence. It takes one picture, then another, and then not focusing particularly on things, although sometimes it's aiming towards just stars, or sometimes it's sampling galaxies. Either way, if it's working the galaxy mode, often they put one of these things over. This is a aluminium plate with little holes drilled in it, with my hand there to scale, and fiber optics on the other side of the holes, and they capture light from the objects you're looking at. So in this case, I think it was looking at galaxies, so they drilled holes in this plate precisely where they were expecting galaxies to be. The fiber optics can take it from there, and we can get images or spectra of the galaxies, sort of 300 or 400 at a time. So that's quite convenient if you're doing a lot of stuff, if you're not wanting to look at something specific. Now for something different, this is the Large Binocular Telescope. So this is like a pair of binoculars working. It's got two large mirrors, each of 8¼ or nearly 8½ meters across. Gives you sort of 22 meters effective view, but only in one direction. So it's 8 meters in one, sort of vertical, and 22 meters-ish in the horizontal. So the resulting image is a little distorted in the resolution. It has more resolution going across than top to bottom. Here's an inside view of it with its two beady eyes staring out. So it's been used for lots of things. This is a picture of, I think this is Io, looking at a volcanic lake in infrared, but a very good image from the ground through fuzzy atmosphere of Io. Yeah, Large Binocular Telescope. Next one, this is European Space Agency, European Southern Observatory, sorry, not Space Agency, ESO. The VLTs, I usually get people to try and guess what these are, but that's a bit redundant here. So this is the very large telescopes, 4 of them, and we can see at least 3 of them there. And they also have these little telescopes here that are used sometimes with the interferometry. So it can either work as 4 independent telescopes, which is how it works most of the time, or it can work as a single telescope working all together, where all the light is pulled together underground through fiber optic ducts. And these little telescopes here out in front, they sort of fill in any gaps that would appear. So this is when you want the really, really precise resolution. So here's the 4 VLTs. One with a laser, which has now been upgraded. I think there's now at least 2 lasers on it, and maybe 4. So you can see this figure down here. This is the arc seconds that it's got. So this is less than an arc second of viewing. And the figure below that is if all 4 are working together. This is the resolution you get, which is extremely fine. But you're really limited by the atmosphere in this case, not by the telescope. And this is a sample of adaptive optics, an animation of that. So this is what the lasers are used for. They shine the laser up to make a stable star bouncing off sodium ions in the atmosphere. And because they know that should be rock solid, but it's actually wobbling around when viewed, with a fast enough computer program, you can take out that wobble and reduce it, and you get back what you really wanted. This is done. This particular one's done in the infrared. It's much easier in the infrared than optical, but we're getting to optical abilities now. And this is going to be key for the bigger telescopes that I'm going to talk about in the future, because they're already limited by the atmosphere. So if you can't take out the atmosphere, you're not really helping the resolution any. This is a picture that they took of Betelgeuse. This is a few years back before it went through its dimming phase, but you can actually see a disk there, so you can get quite good results. These are a couple of the biggest telescopes in the planet currently, just less than the biggest. These are 2 10-meter Keck telescopes, and these use slightly different mirrors. The VLTs are solid mirrors, 8-meter mirrors. The Keck ones are these assembled mirrors of hexagonal plates all stuck together. And this is the way all sort of modern telescopes are now being constructed, because you just can't. Well, not quite, actually. We'll come back to that. There are largely this is how you now construct them, because they have a lot of benefits. Firstly, you can build them almost to any size, because you can just keep on adding hexagons, basically, provided you've got the space. Another good feature of this is your mirrors need cleaning every now and again. And with this sort of setup, you just take out one hexagon, you clean it, you put it back, you take out the next hexagon, and your telescope is still usable. So it's a good way to go. In radio telescopes, well, this is sort of somewhere in between classical radio and optical. This is millimeter observations. So this is the ALMA telescope, which is 66 radio telescopes working in the air. Sub-millimeter and millimeter. These are particularly good at looking at infrared objects and anything that's giving off millimeter wave radiation. So when working together in certain concert, and you can spread them out or join them together depending on how you want to observe your target, they have about 5 times the resolution of Hubble. And this is one of the more famous images we've got from that. This is a planetary disk in formation. So we can see the sun at the center of this, and we can see these sort of rings etched out of the planetary disk, which we expect our planets partway through forming. Of course, we can go to radio, and this is the Jodrell bank. I hope everybody has seen the Jodrell bank at some point in their life. 76 meters. And this goes back to that equation I showed you. Because we're now working at long wavelengths, you really need a huge aperture, and even a 76 meter aperture gives you nowhere close to the optical resolution. So you're really sort of hamstrung when you get to radio waves to get a big enough aperture to see very much. So you can go much bigger. This is the Arecibo bowl that you may well have seen or heard of. It's appeared in 2 or 3 films, certainly in Contact, or I think in one of the James Bond films. It's mostly fixed because it's in a sort of valley pointing straight up, but you can move the receiving horn, which is this bit up here. You can move that around a little to try and track objects for a short while. This has been taken to the extreme in China by the FAST, or 500 meter aperture spherical telescope. Something that's almost completely wrong in every part apart from the telescope bit, which is probably the biggest radio telescope that's ever going to be built. Here's an image of it almost complete. It is now complete and actually operational. So although it's 500 meters, which is half a kilometer, it actually only uses 300 meters at any one time, because it uses part of the dish to focus whatever it's looking at. And I believe the dish is actually parabolic, not spherical. So there we go, but why let that ruin a good acronym? So just to compare, these are the different sizes of the telescopes. You can see there, Jodrell bank on the left at 76 meters and FAST on the right at 500 meters. So pretty good coverage. Then we go to space telescopes. Now, why would we go to space telescopes? There are a number of reasons. I've already talked about the pesky atmosphere getting in the way. That's certainly one reason. Another one shown by this Wikipedia image is just that the atmosphere blocks completely some radiation. So up at this end of the spectrum, this is the high energy end with X-rays, gamma rays and ultraviolet. The atmosphere blocks nearly all of that. Obviously, we can see in the visible, we can see in the infrared at certain wavelengths. The far infrared, that's not very good. Things are there. Somewhere around there is completely blocked on Earth, so we can't see any of that. Then we have the radio hole here that lets us look in radio waves, but only up to a limit. These very long wavelength radio waves are blocked. So up at this end here, this is the rays are just so energetic, they ionize the atmosphere and they get absorbed. which is good because most of this radiation is pretty deadly. In this middle part, it's usually molecules in the atmosphere, water, methane, carbon dioxide. They just absorb radiation. And we're picking out certain things here that are absorbing these spikes. And at this point, down at the far end, this is just long radiation, just bounces off the atmosphere. The ionosphere just bounces it off back into space. So that's why we're kind of stuck with that. So the first reason to go above the atmosphere is it's much clearer. We don't get weather, we don't get day and night, we get no atmosphere in the way. So Hubble, obviously famous for its observations, we get the full resolution of its diameter and 0.05 arc seconds of resolution. So that's why Hubble with its 2.4 meter mirror is so good. It's just got perfect conditions all the time and can take iconic photographs like this. As I'm sure everybody's seen the Pillars of Creation. If you go to long wave short wavelengths, X-ray in particular, we currently have two operational telescopes, XMM Newton and Chandra, both working above the atmosphere because X-rays are absorbed. And we can look at very energetic objects like black holes and certain stars with this. So this is just showing you again how technology moves on. This is an earlier X-ray telescope called ROSAT, looking at the Crab Nebula. You can see there it's quite bright in the middle. There's some structure going on there, but it's not really clear what's happening. When we go to a more modern view, XMM Newton, I think this one is, you can see there spirals of stuff and a jet coming out. Suddenly, the shades are lifted and we can see so much more detail. When I originally studied physics quite a few years ago now, we couldn't actually focus X-rays. I remember a lecturer saying, you just can't focus X-rays. We don't have lenses for them. Well, nowadays we do, up to a point. This is my crummy diagram of a mirror. These are the atoms in it. So we've got a whole load of atoms there. And when the atom spacing is much bigger than the wavelength of light, which it is in this case, the light effectively sees a solid wall and just sort of bounces off it. He said, hand-wavingly, going through the explanation. When you get to X-rays, they're so tiny, they just effectively fit between the atoms and go straight through. And this is why X-rays go through most material. Very dense material tends to soak it up, but it doesn't tend to reflect it. But what we do now is have these things called grazing instance mirrors, which is if the X-rays come in at a very, very shallow angle of about 1 degree to the mirror, they effectively see it as a sort of very long plane. So it's very much like skimming stones across a lake. If you skim them at a very fine angle, they bounce off the lake and carry on out into the, they bounce off and carry on. If you sort of throw them up and they come straight down, they just plop into the lake. And it's a very similar story here. So this is what an X-ray telescope looks like. It's a concentric ring of usually glass mirrors, so they're called. And the X-rays come in at a very fine angle and they sort of shimmy off them and they bounce toward the focus and are collected. If you go up much higher or you go to very hard X-rays, energetic, you can't do this trick. And gamma rays are sort of X-rays on steroids, so they go through almost everything. And all you can do there is what you do with typical hospital X-rays. You just make a shadow picture, basically. So you have a structure here that makes a shadow of the gamma rays coming in, and you can see sort of a projected image. And if you pick this mask carefully, you can actually do 2 or 3 directions at once. So that's one way to take gamma rays. And then you also have to do fiddly stuff with the gamma rays because they're so energetic. You have to sort of slow them down and produce electrons. But you can see this is a picture of the night sky in gamma rays, and you can see this bit across the middle here is the plane of the galaxy. And these bits up here are called Fermi bubbles, and we didn't know they existed until we looked at them with gamma rays. We're not quite sure what is responsible from those, although we have a few suggestions perhaps. Then if we come down the spectrum, Spitzer is an infrared telescope. I think it's still working. I've got a feeling it might just have finished recently, but it's been working for many years. The problem with infrared telescopes is when you look at infrared, you're basically looking at heat. So if you're not careful, you'll look at anything that's giving off heat, and the telescope itself will give off heat. So you have to cool them down really to very cold temperatures to let them do their job. So they nearly always launch with liquid nitrogen on, or liquid helium, or both, to keep the telescope cold. And that eventually boils away, and after that, depending on the telescope, it may or may not be useless. Spitzer, this happened to quite some time ago, and now it's sort of working in what's called the warm phase. And if it's still working, I've got a feeling it's stopped working now. But then it can only work on certain objects because everything else is too warm. But you can look at things like this. This is a galaxy, and you're looking in particular at the stuff that's giving off infrared radiation, the dust in this case. Herschel was far infrared, and if you remember back to the diagram of what goes through the Earth's atmosphere, nothing goes through in the far infrared. So while you could look in some of the areas that Spitzer was looking, you can't look in any of them, Herschel. And Herschel really completed the infrared picture. But this did need keeping very cold, and soon ran out of cryocoolant and was launched out of where it was into a solar orbit. I think this had the biggest mirror so far, a space telescope at 3.5 meters. Soon to be overtaken, hopefully. Famously, Kepler, looking for planets, looking around here, around Cygnus, and discovered somewhere around 4,000 planetary candidates, of which I think about 1,500 have been confirmed, and the others are still being followed up. Because it's in space, it doesn't have any problem with the seeing, and dips in light, which is what it's looking for very faint changes in light from stars. Because it's in space, it can do that. Gaia is another one that this one is measuring distance to about 1 billion stars in the Milky Way, and also measuring their velocities. Has a very large camera there of 1 gigapixels, but is sort of making a cosmic map of the Milky Way for us to use, and reaches out quite a long way. You can see here from one of their publicity pictures how far it's going. So off into the central core of the galaxy and beyond, also out to the Magellanic Clouds. And we will have very precise distances to stars and their velocities out to that sort of distance. So with that, I'm going to sort of devote the rest of the talk to future telescopes and what's to come. So I'm going to start with the biggest. The biggest one is the ELT, the Extremely Large Telescope, or the European Extremely Large Telescope, as I think it was called for a while. I think now they've dropped that and it's just back to ELT. This is the biggest telescope in construction, or indeed planned anywhere on the that we know of, in fact, in the optical at least, as long as we disregard the radio. At nearly 40 meters across, it's a fantastic mirror size. I say it's about somewhere around half a football pitch of mirror that could be pointed anywhere you like. That 2022 date is probably ambitious. I think it's more like 2025 now. But they've built up to somewhere around this level, I think. Till now, they've poured the concrete, they've flattened the mountain, and they are starting to build. So it's in construction now. If you want to see what a 40-meter mirror looks like, here is one laid out. I'm not too sure where, but this is laid out in cardboard on the ground, just to show you just how big a 40-meter mirror is, which is completely vast. This is it in comparison to the pyramids and also to the VLT telescopes, which are down here. So you can see it dwarfs the VLTs. It's on the next mountain along from the VLTs, so extremely large. and weighs around 2,800 tons. So it's a huge beast by any measure. This is it next to Big Ben, and this is its image train. So you can see the large mirror at the bottom. Secondary mirror M2 is, I think, a 4-meter mirror, so pretty big mirror there. And then there's actually 5 mirrors that it bounces between before going off to one of the Naismith's platforms to actually look at the signal. So all sorts of things there. And I think it's either the third or fourth. I think it's the fourth mirror actually that will be the adaptive optics one that I'll come on to talk about. This is a cheeky photograph showing one of the VLTs sitting on the Naismith platform of the ELT. So you could actually put one of the VLTs as an instrument on the ELT. This uses 5 lasers, or at least 4. I think 5 was at one point. So this is, because it's got such a wide field of view, you can't take out all the atmospheric shimmer with just one laser. You need to sample the atmosphere across that whole area. So 4 or 5 lasers needed to work out exactly what's happening to the atmosphere and undo the wobble through the fourth mirror to give you a perfect picture of it. Just a few of the specs there that you can see, made of 798 of these hexagonal mirrors, making up the primary, which would weigh 259 tons. You can see there the size of some of the other mirrors. Each of those is a substantial mirror on its own, and say 2,800 tons of main structure to revolve around and point precisely. So you imagine how the tracking on these must be tweaked and periodically aligned and all that sort of stuff. It's not the only game in town though, although this one is got a rather tricky history. This is the TMT, the 30-meter telescope. That's a clue there that you can see. Sorry, I've just lost a mouse. So this one is supposed to be being built on Hawaii, but unfortunately it's subject to a lot of legal challenges that people don't want to build more telescopes on Hawaii. And although it got through the legal challenges a few times, it's now stuck in sort of legal problems. Every time they think they've got planning permission to go ahead, it gets rejected or challenged or whatever. So they're even considering building this on the Canary Islands instead as a secondary place. So this is what it would look like. Lots of hexagonal mirrors, 30 meters across, much like the ELT, but not quite as big. But still will be the largest telescope in the Northern Hemisphere if it's built, if it gets through its challenges. This is the other big telescope being built. This is the GMT, Grand Magellan Telescope, GMT. And this one you can see they've gone more conventional with 6 8-meter mirrors and another 8-meter mirror in the middle that is got a hole through it, like a sort of Cassegrain type thing. So this is a bit like the binocular telescope, where you're bringing lots of mirrors together to become greater than the sum of its parts, sort of thing. So depending on how you count it, this could be a 24-meter or a 22-meter mirror. Certainly the 2020 is very ambitious for that. 2026 is probably about the same time as the ELT will be produced. This is one of its mirrors being built in the Arizona Mirror Lab, which is underneath their football stadium at Arizona University. You can see there what goes into an 8-meter mirror. And 8 meters is, they could probably build it a little bigger. They think they could probably go to 10-meter mirrors, but the logistics of moving around an 8-meter mirror are tricky enough. You've got to find bridges that will go under, ships that will carry it, and all that sort of stuff. So 8 meters is about as big as they want to go at this point. So this is an artist's conception of what the GMT will look like. This is also being built in Chile. Not in a similar region to the ELT and the VLTs. It's a very good place to build things. This is another big one. I think this is also being built in Chile. This is the LSST, but has been renamed Vera Rubin Telescope. So it used to be Large Synoptic Survey Telescope. So this very much like the first one I started with, the SDSS, the Sloan Digital Sky Survey. This is another survey telescope, but this one is optimized to go around the sky at high speed. It will take, it's got an 8-meter mirror, but a 3.2 gigapixel camera, and produces about 15, or will do, it's getting close to being finished now, 15 terabytes of images a night. So that's a substantial amount of stuff. So once this gets up and going, there's not going to be many astronomers looking at the images it takes. There's just going to be far too many of them. So we're writing computer programs to look at these. Here's its camera with a picture of the full moon on, so you can see how huge its camera is and how much of the sky it can take at once. So the idea is that it takes a 15-second exposure with this 8-meter camera, and then 20 seconds to move to the next position, then another one, and just zaps around the sky. And then you compare last night's image with this night's, look for supernovas, anything moving such as asteroids, planets, anything like that. So a great way of surveying the night sky. The next big thing in radio telescopes is the square kilometre array. So this is, you say we've got to about the limit with the 500-meter radio telescope in China. So another way to build a much bigger telescope is to build it in parts, much like we've seen with the segmented mirrors. You put lots and lots of radio dishes around, and then you join them up and you do some clever computer analysis to join them all. So square kilometre array is going to be all across South Africa and Western Australia. And so we'll sort of get continent-sized images from these ones. And it's called the square kilometre array because if you add up the collecting area of all the telescopes, it comes to 1 kilometre square overall. Next thing in space is the James Webb Space Telescope, which is here. It should have been launched this year, should have been launched last year. Is pretty much the story going back from quite a while. This is a 6.5 meter mirror, so much larger than Hubble's. Very good resolution. This is primarily going to work in the near infrared and the red end of the optical spectrum. So it's not quite a replacement for the Hubble Space Telescope, but it's going to be fantastic. Lots of astronomers want to get their hands on this. But there is one problem with this. You can see how big it is there compared to the people. You can't put something that big in a rocket. Not even the space shuttle could fit that in. So you have to fold it up into something like this. This is what you can fit inside the nose cone of a rocket and launch into space. And then you have to unfold it. And this is one of the reasons it's been so delayed. You have to go through this step of about 300 operations in space with nobody helping it. And it all has to happen perfectly. This is the sunshade folding out to protect it. This telescope was originally proposed in 1995, I believe, at the cost of about $500 million, designed to fly in about 2005, and it's now cost over $8.5 billion, and hopefully it will launch next year, as long as the current crisis hasn't affected it too much. It's way behind schedule, way over budget, and has really eaten into a lot of NASA's plans. So they had lots of missions they wanted to do, but each time, you've got to fund the JWST because it's already taken $4 billion. We're not going to throw that away. Just another $500 million and it will be ready to launch, but that keeps going on and on. And here we are, $8.5 billion. But looks like we're really close this time. Another interesting telescope, WFIRST. This was a mission that was planned quite some time ago and to look for all sorts of things, particularly the expansion of the universe. But they got lucky with the American Spy Agency. They happened to have a couple of Hubble scale telescopes that they weren't going to launch. So they said, could you use these? And so WFIRST was now adapted from what was going to be a custom designed telescope to use one of these things, because it's already got a couple of mirrors ready to go and all the other bits. It needs some work still to be done, so it's not completely free, but it does give you a huge step up. So WFIRST is one of those things. Scheduled for sometime in the next 2025, 2028, sometime like that. And it could possibly work with this next thing, which is called a star shade, which is this sort of very flowery thing that flies on its own. And the idea here is you go and move this around so it will sit in front of a star, and you can then image the star, or at least the planets are going around it, with the star's radiation blocked out. It would probably take about a week to get into position each time, so it's not a particularly fast thing, but it's somewhat better than doing the blocking out internally. But there are big question marks over whether this will ever fly. But if it does, things like the James Webb and WFIRST want to make use of it, so they are sort of keeping it in mind that they could use it. These are two planet hunters. One of these actually already launched. Cheops is already launched, looking for exoplanets. But Plato is still scheduled to go up to 2026. These are both ESA missions, I believe, to look for more exoplanets. Now we know what we're looking for in detail. We can go off and look with dedicated telescopes looking for specific things. Oh, and that's come to the end of the talk. So thank you very much for listening. I'm really sorry about the sound that I got that wrong to begin with. If you've got any questions in the chat, I'm really happy to have a go at asking for them. Otherwise, if you hang around till 8:30, we've got Pete Williamson on Astro Radio and the lock-in session going on there. So welcome to join astroradio.earth to listen to all that. But otherwise, I'm kind of done here if you don't have any questions. The trouble with this format is there's about a 30-second delay between what I say and what appears in the chat. So I'm just going to carry on filling a bit of time waiting to see if there's any specific questions. Otherwise, I hope it came out. And again, very sorry about the audio issues early on. I should have checked on that earlier. I did do one quick check beforehand, but then forgot to reset the button. So, hope you're all safe and well up there in North Wales and wherever else you're looking. You've all got good supplies of toilet roll, flour, pasta, and anything else. And I'm happy to do this again for any other societies who might be listening in or on any other subject. I'm writing a couple of new ones, one about the solar system, and I've just done one about the exploration of Venus. Good question, Matthew Foyle. No, I don't have any cake at the moment. That's sadly lacking. But thank you for the question. I shall go and see what I can raid. I think there's a slice of cheesecake left in the fridge, so I'm going to go and have a look at that. Good question about cake. Yes, thank you, Tracy. Yeah, so I'm going to raid the fridge shortly and see what I can find in there. So I suspect an Easter egg will also fit in for cake at this juncture too. Well, what time have we got to now? 8:20. So I managed to squeeze that in. It finished a little more abruptly than I thought it was. I thought I got a couple more slides there. I must have cut some out. Right, Tracy has a question. If you had time on any telescope, which scope would you look for? Um, we've actually discussed this a couple of times in the astronomy department over cake, which we have on a Friday afternoon. I'm missing that very much at the moment. So we all sit around at 4 o'clock, have some cake that people make, and discuss weighty issues of the day. And one was, which telescope would you like to look through? And our head of department, Mike Merrifield, said he would very much like to look through the ELT. He thinks they're missing a trick by not putting an eyepiece to the focal plane of the ELT and being able to look through it. I'm not quite sure what you'd see. I imagine it'd be very bright, but he thinks it would be an excellent PR exercise just to be able to say you looked through a 40-meter telescope. He did tell me he'd once looked through one of the Isaac Newton group telescopes on La Palma that they were doing. Normally it's a camera or a spectroscope connected up to it, but one time when they were doing some maintenance or something, they needed to check that it was all clear or something, so they put an eyepiece to it. So I think that was probably a sort of 1 to 2 meter size telescope that they used that with. So yeah, pretty good. Right, well, thank you all for coming, and yes, a big eyepiece certainly. So thank you all for coming. I'm going to end it here so that we can all shimmy over to astroradio.earth and get in. I think there's another quiz tonight, is there? I can't remember. There's a live performance tomorrow night, I know, of Herschel to Hawkwind, so that will be interesting. So worth a listen to that. So thank you all for coming, and perhaps see you again soon. Cheers when all this is over.